Right now, at this very moment, a small robotic rover is crawling across a rust-colored desert more than 200 million kilometers away, taking photographs of a world where the wind blows, but no ear has ever heard it, where the sky glows pink at dusk, and the sun rises small and pale over ancient mountains taller than any on Earth. A place called Mars, the silent red neighbor that has watched our pale blue world for billions of years. Tonight, we explore the red planet, that distant, dusty world that has fascinated stargazers, scientists, and dreamers for centuries. It is a place of extremes and quiet beauty, where towering volcanoes sleep beneath pink skies and frozen deserts stretch toward horizons no human has ever touched. Welcome to Drowsy Discovery. Over the next 2 hours, over 100 gentle facts will drift toward you like dust settling on Martian plains. There is nothing to memorize, nothing to remember. Just listen and let your mind drift. Have you ever gazed at a glowing red dot in the night sky and wondered what it would feel like to stand on its surface? You are not alone. If this journey brings you comfort tonight, a simple subscription helps us share this peace with others who cannot sleep, building a community of curious minds, one restful night at a time. Now let your shoulders drop just a little, let your jaw unclench, and take a slow breath in, then out again, like the faint Martian breeze stirring ancient dust. There is nowhere you need to be, nothing you need to do. The red planet is waiting, patient and still, just as it has waited for billions of years. Let us begin. Mars is the fourth planet from the Sun, drifting through space in a quiet orbit between Earth and the asteroid belt. Mars traces a slow, elliptical path around the Sun at an average distance of roughly 228 million kilometers, taking its place as the outermost of the rocky inner planets, a world of stone and dust rather than the swirling gases that dominate the outer solar system. It orbits in a region where sunlight is noticeably weaker than what falls upon Earth, receiving only about 43% of the solar energy that warms our own world. And yet this faint light is enough to illuminate a landscape of deserts and mountains that has remained largely unchanged for billions of years. Beyond Mars lies the asteroid belt, a scattered ring of rocky fragments that never coalesced into a planet. And further still, the gas giants begin their cold dominion. Mars sits at a boundary, the last of the small terrestrial worlds before the vast outer darkness, a quiet sentinel between two realms. A single day on Mars is only 37 minutes longer than a day on Earth. The Martian day, called a sol, lasts approximately 24 hours and 37 minutes, so close to an Earth day that a human living there would hardly need to adjust their sleep schedule, waking and resting in a rhythm that would feel almost familiar. This similarity is not by design, but by coincidence, the result of how each planet formed and spun in the early chaos of the solar system. And it means that sunrise and sunset on Mars follow a pattern that would feel strangely homelike to anyone watching from its dusty surface. Engineers working with Mars rovers often shift their schedules to match Martian time, living by sols rather than hours, their body clocks gradually drifting out of sync with everyone else on Earth. It is a small comfort for future explorers, this near matching of days, a thread of familiarity woven into an otherwise alien world. Time, at least, would feel almost like home. Mars has only 1/3 of Earth's gravity, meaning you could jump 3 times higher there than you can here. Standing on the surface of Mars, you would weigh only about 38% of what you weigh on Earth, your body suddenly lighter, your steps springier, and any effort to jump would send you soaring to heights that would seem almost dreamlike compared to the leaden pull of your home planet. This weaker gravity arises because Mars is smaller and less dense than Earth, lacking the heavy iron core that gives our world its substantial mass, and it shapes everything about the Martian landscape, from the towering heights of its volcanoes to the way dust settles slowly back to the ground after being disturbed. Astronauts who eventually walk there will need to learn a new way of moving, calibrating their muscles to a world where every step covers more ground and every object feels surprisingly easy to lift. It is a world where the body becomes lighter, but the distances remain vast. Weight becomes an illusion. The red color of Mars comes from iron oxide dust covering its surface, the same compound that makes rust on Earth. The distinctive rusty hue that gives Mars its name as the red planet comes from iron oxide particles blanketing nearly every visible surface, a fine dust that has accumulated over billions of years as iron-rich rocks weathered and oxidized in the presence of oxygen atoms released from water and carbon dioxide long ago. This is the same chemical reaction that turns a forgotten iron nail orange-brown in a damp garden, but stretched across an entire world and deepened by eons of slow transformation under alien skies. The color is not uniform everywhere, shifting from bright orange in some regions to darker browns and even purplish tones where different minerals dominate. Yet the overall impression from space is unmistakably red, a world that looks as though it has been gently rusting since the beginning of time. It is a color that ancient humans associated with blood and war, naming the planet after gods of conflict. The rust of ages painted across a silent world. Mars is roughly half the size of Earth, yet it holds landscapes that dwarf anything on our home planet. With a diameter of about 6,779 kilometers, Mars is only slightly more than half the width of Earth, a smaller sibling in the family of rocky planets. Yet within this modest frame are compressed features of such staggering scale that nothing on our own world can compare. The tallest mountain, the deepest canyon, the largest known impact basin in the solar system, all of these belong to Mars, as though the planet compensated for its smaller size by building everything on a grander scale. The lack of plate tectonics allowed volcanoes to grow uninterrupted for billions of years, and the lower gravity permitted canyons to stretch wider and deeper than anything Earth's restless crust could sustain. It is a paradox written in stone and dust, a world that seems modest from a distance yet reveals its immensity to anyone who looks closely. Small in stature, vast in presence. A year on Mars lasts 687 Earth days, nearly twice as long as our own. Because Mars orbits farther from the Sun than Earth does, it travels a longer path and moves more slowly through space, taking 687 Earth days to complete a single journey around our star, a Martian year that stretches nearly twice as long as the one we measure by seasons and calendars. This extended orbit means that any future colonists would experience seasons that linger for months longer than they do on Earth, winters that seem endless and summers that stretch across what would feel like nearly 2 terrestrial years. The planet's elliptical orbit also causes more dramatic variation in distance from the Sun throughout the year, making some seasons notably warmer or colder than others in ways that feel less balanced than Earth's relatively circular path. Time would flow differently on Mars, marked by patient seasons and slow-turning years, a longer dance around the same distant star. Mars is tilted on its axis at almost the same angle as Earth, giving it 4 distinct seasons. The axis of Mars is tilted at approximately 25 degrees relative to its orbital plane, remarkably close to Earth's own tilt of about 23.5 degrees. And this similarity means that Mars experiences seasons in much the same way we do, with hemispheres leaning toward or away from the Sun as the planet orbits, bringing warmer summers and colder winters in a familiar rhythm. The northern hemisphere enjoys a long, mild summer, while the south endures a brief but more intense one, and dust storms tend to begin during the southern summer when the planet is closest to the sun and heating is most uneven. Unlike Earth, where oceans moderate temperature swings and forests change color, Martian seasons are marked more by shifts in dust activity and the expansion or retreat of the polar ice caps. Yet the fundamental pattern is the same, a world tilted just enough to experience the ancient rhythm of changing seasons, summer and winter, even on a world so far from home. The average temperature on Mars is -60 degrees Celsius, colder than any natural place on Earth. The surface of Mars averages a frigid -60 degrees Celsius, far colder than the most bitter winter night in Antarctica, a world where exposed human skin would suffer frostbite within minutes, and where breath would crystallize instantly in the thin, dry air. This extreme cold arises from the planet's greater distance from the sun, combined with its thin atmosphere, which cannot trap heat the way Earth's dense blanket of air does, allowing warmth to radiate away into space almost as quickly as it arrives. At the equator on a summer afternoon, temperatures can briefly climb above freezing, touching perhaps 20 degrees Celsius in sheltered spots, but as soon as the sun dips toward the horizon, the warmth vanishes, plunging back toward the deep cold that is Mars's baseline state. Night brings temperatures that can fall below -100 degrees Celsius in some regions, a world locked in perpetual winter's grip. And from these fundamental truths about the red planet, we now turn our gaze downward to the ancient and weathered surface beneath the Martian sky. The surface of Mars is covered in a fine dust called regolith, billions of years of broken rock and weathered stone. The ground beneath your feet on Mars would not be soil in any earthly sense, but rather regolith, a layer of fine particles created over billions of years as rocks were shattered by meteorite impacts, cracked by extreme temperature swings, and slowly ground into dust by the thin winds that sweep across the surface. This material ranges from fine powder that clings to everything it touches to larger pebbles and chunks of fractite scattered across the landscape, and it covers the planet so completely that finding exposed bedrock requires looking to crater walls or canyon edges where gravity has swept the dust away. Unlike Earth's soil, which is alive with organic matter, bacteria, and the roots of countless plants, Martian regolith is sterile and dry, a purely mineral blanket untouched by life as far as we know. It shifts and settles and coats every rover that has ever landed, the quiet accumulation of 4 billion years. Mars has the largest known impact crater in the solar system, the Hellas Basin, stretching over 2,000 kilometers wide. The Hellas Planitia is a colossal impact basin carved into the southern hemisphere of Mars by an asteroid or comet struck roughly 4 billion years ago, measuring over 2,000 kilometers in diameter and plunging more than 7 kilometers below the surrounding terrain at its deepest point, so vast that it could swallow entire mountain ranges with room to spare. The impact that created it must have been one of the most violent events in the early solar system, releasing energy beyond anything humans have ever witnessed, reshaping the entire region and sending debris scattering across half the planet. Today, the basin holds some of the thickest atmosphere on Mars, its low elevation allowing air pressure to climb slightly higher than elsewhere, and dust storms often form within its sheltered walls before spreading outward across the globe. It is a scar from the violent youth of the solar system, still visible after eons, the mark of an ancient cataclysm. The northern hemisphere of Mars is mostly flat lowlands, while the southern hemisphere is covered in ancient cratered highlands. One of the most striking features of Mars when viewed from orbit is the dramatic difference between its two hemispheres, with the north dominated by smooth, relatively young lowland plains that lie several kilometers below the average surface level, while the south is a rugged expanse of ancient highlands pockmarked with craters from the earliest era of the solar system. This dichotomy has puzzled planetary scientists for decades, with theories ranging from a single catastrophic impact that stripped away the northern crust to internal processes that caused the crust to thin in one hemisphere, and no single explanation has yet satisfied everyone. The boundary between these two regions is marked by a gradual slope in some places and by steep escarpments in others, a visible seam running roughly around the planet. It is as though Mars is two worlds joined together. A planet of contrasts written across its face. Some regions of Mars are covered in dark basaltic sand, forming dunes that shift slowly with the thin Martian wind. Scattered across the lowlands, and within many craters of Mars, lie fields of dark sand dunes, their color a deep gray or black that stands in stark contrast to the rust-red soil that dominates most of the landscape. Composed of basaltic grains eroded from ancient volcanic rocks and carried by winds too thin to feel yet persistent enough to move particles grain by grain across the centuries. These dunes form ripples and crescents and long sinuous ridges that resemble the sand seas of the Sahara or the Namib, shaped by the same physics that governs dune formation on Earth, but stretched across timescales that dwarf human history. Spacecraft have photographed these dunes shifting over the course of years, proving that the surface of Mars is not entirely frozen in time, but continues to evolve, if far more slowly than we might expect. The wind still sculpts, the sand still moves. A desert that has not forgotten how to breathe. The soil of Mars contains perchlorates, chemical compounds that make it toxic to most Earth life as we know it. Mixed into the fine regolith that blankets Mars are perchlorate salts, reactive chemical compounds containing chlorine and oxygen that would be highly toxic to most life forms from Earth, disrupting thyroid function in humans and chemically attacking organic molecules in ways that make the soil hostile to any bacteria we might accidentally carry there. These perchlorates form naturally on Mars through interactions between ultraviolet light and chlorine-bearing minerals, accumulating over millions of years in concentrations far higher than would be found in any natural environment on Earth. For future colonists hoping to grow food in Martian soil, removal of these compounds would be essential, adding another challenge to the already formidable task of making human life sustainable on a world so fundamentally different from our own. The red dust looks almost welcoming, yet it carries chemistry that would sting and burn. Dust devils on Mars can rise kilometers into the air, towering columns of spinning dust that leave dark trails on the surface. On warm Martian afternoons, when sunlight heats the ground unevenly, columns of spinning air can form and lift the fine surface dust into rotating vortices that tower kilometers into the pink sky. Dust devils far larger than any seen on Earth, their funnels visible from orbit as dark shadows crawling across the landscape. Though the thin Martian atmosphere means these vortices carry little force, they can still clean solar panels on rovers by stripping away accumulated dust, and they leave behind dark streaks on the surface where lighter-colored dust has been swept away to reveal the darker rock beneath. Rovers have photographed hundreds of these spinning columns on the horizon, ghostly shapes that drift silently across the terrain before dissipating as quickly as they formed. They are the closest thing to weather that Mars experiences on most days, quiet whirlwinds dancing in the afternoon light. The surface of Mars has not been reshaped by plate tectonics for billions of years, preserving ancient landscapes untouched by geological renewal. Unlike Earth, where the surface is constantly recycled by the shifting of tectonic plates, Mars appears to have had little or no plate activity for billions of years, leaving its surface as a frozen record of ancient geological events that would have long since been erased on our own dynamic planet. Craters from the earliest bombardment phase of the solar system remain visible on the southern highlands, their rims softened by wind erosion, but otherwise unchanged since impacts that occurred before the first life arose on Earth. Volcanoes grew where they formed rather than being carried away on drifting plates. Mountains remained where they were first uplifted, and the great canyons held their shape without being compressed or subducted into the mantle. This stillness is both a blessing and a limitation for scientists, a world that remembers its own youth. And as you rest with these images of ancient Martian plains, there is no need to hold onto anything. Let each fact drift past you like red dust on a distant wind. Take a slow breath and let your body settle a little deeper. Now let us lift our gaze from the dusty ground and look upward into the thin veil of atmosphere that wraps around the red planet. The atmosphere of Mars is 95% carbon dioxide, with only trace amounts of nitrogen and argon. The thin envelope of gas surrounding Mars is overwhelmingly composed of carbon dioxide, making up roughly 95% of the atmosphere, with the remaining few percent divided between nitrogen, argon, and tiny traces of oxygen, water vapor, and other gases. On Earth, carbon dioxide comprises only a fraction of 1% of our air, yet on Mars it dominates so completely that breathing outside a sealed habitat would be impossible, not only because of the wrong composition, but because the pressure is so low that lungs would not function properly. This carbon dioxide atmosphere once may have been thicker, perhaps thick enough to keep the planet warm and wet, but over billions of years, much of it was stripped away by the solar wind or locked into the polar ice caps and surface rocks. What remains is barely enough to call an atmosphere at all, a whisper of air around a silent world. The atmospheric pressure on Mars is less than 1% of Earth's, so thin that liquid water boils away almost instantly on the surface. At the surface of Mars, the atmospheric pressure averages about 600 pascals, less than 1% of the sea level pressure on Earth, a near vacuum by human standards that would cause any exposed liquid water to boil violently and evaporate within seconds, not from heat, but from the simple absence of pressure to hold the molecules together. This extreme thinness means that sound travels poorly on Mars, that winds carrying tremendous speed deliver only a gentle push, and that any human standing unprotected would experience something similar to the near vacuum of space, with blood beginning to boil at body temperature and consciousness fading within moments. The low pressure also affects how vehicles and habitats must be designed, requiring strong pressure vessels and airlocks to maintain the dense, oxygen-rich environments humans need to survive. It is an atmosphere in name only, too thin to breathe, too thin even to hold water. The sky on Mars appears butterscotch or salmon pink during the day because of fine dust particles suspended in the atmosphere. If you stood on the surface of Mars and looked up at midday, you would not see the familiar blue sky of Earth, but rather a hazy expanse of butterscotch, salmon, or pale orange, the color shifting depending on how much dust hangs suspended in the air and the angle of the sunlight passing through. This distinctive hue arises because the fine iron-rich dust particles that fill the Martian atmosphere scatter red and orange wavelengths of light much more efficiently than the blue wavelengths that color Earth's sky, creating an effect precisely opposite to what we experience at home. The color deepens during dust storms when the air becomes so thick with particles that visibility drops to meters, and the sky takes on an almost uniform tan, and it lightens on clear days when the dust settles and the sky becomes a paler, almost peachy shade. It is a sky unlike any other in the solar system, painted in rust and silence. Sunsets on Mars glow blue instead of red, the opposite of what we see here on Earth. In one of the strange reversals that make Mars feel like a mirror image of our own world, sunsets there glow with soft blue light, rather than the fiery oranges and reds we see when our own sun dips below the horizon, a phenomenon captured by rovers and cameras and sent back across millions of kilometers to astonish everyone who sees it. This blue coloration occurs because the fine dust particles in the Martian atmosphere are just the right size to scatter blue light forward in the direction you are looking, while longer red wavelengths scatter off to the sides, the precise opposite of how larger particles in Earth's atmosphere create our golden sunsets. The effect is subtle but unmistakable, a cool blue glow surrounding the small, distant disk of the sun as it sinks toward the dusty horizon, fading gradually into the deepening pink of the Martian dusk. Evening there would feel strange and beautiful, the day ending in blue instead of gold. Thin clouds of water ice sometimes drift through the Martian sky, fragile wisps against the pale horizon. Despite the extreme dryness of the Martian atmosphere, thin clouds of water ice occasionally form at high altitudes, wispy formations that drift across the pink sky like the faintest cirrus clouds on Earth, so delicate that they seem almost accidental condensation from the tiny amount of moisture that remains in the Martian air. These clouds form most commonly near the poles during winter and at certain times over the great volcanoes of Tharsis, where air rising over the mountains cools enough for ice crystals to precipitate, catching the light of the distant sun and glowing faintly against the darker sky. Rovers have photographed them at dawn and dusk, when the angle of light makes them easier to see, recording their slow drift across the field of view like memories of a time when clouds were thicker and rain perhaps fell on younger Martian soil. They are fragile reminders of water that once was plentiful, ghosts of a wetter past. The winds on Mars can reach speeds of over 100 kilometers per hour, yet they feel like a gentle breeze because of the thin air. Wind speeds on Mars can climb remarkably high, sometimes exceeding 100 kilometers per hour during major dust storms, velocities that on Earth would snap tree branches and send unsecured objects tumbling through the air. Yet on Mars, these same winds feel more like a gentle breeze, barely enough to stir the hair on your arm, because the atmosphere is so thin that even fast-moving air carries very little force. The density of the Martian atmosphere is less than 1% of Earth's, meaning that a wind moving at storm speed delivers roughly the same push as a light breeze on a summer afternoon at home, gentle enough that early mission planners worried about it unnecessarily, imagining rovers toppled and habitats torn apart by forces that turned out to be almost negligible. The wind can still lift dust, still pile sand into dunes, still polish rocks over millions of years. But it whispers rather than roars, fierce in speed, gentle in touch. Mars experiences massive dust storms that can engulf the entire planet for weeks or even months at a time. Roughly every few Martian years, conditions align to trigger a planetary-scale dust storm that begins in one region and rapidly spreads until the entire globe is wrapped in a haze so thick that surface features become invisible from orbit, a shroud of orange-brown particles that can persist for weeks or even months before finally settling back to the ground. These global storms typically begin during southern hemisphere summer, when the planet is closest to the sun and heating is most intense. The warm air-lifting dust that absorbs more sunlight and lifts more dust in a self-reinforcing cycle that can raise particles tens of kilometers into the atmosphere. For solar-powered rovers, such storms can be devastating, blocking the sunlight they depend upon and forcing them into hibernation, or, in the case of opportunity, into a permanent silence from which they never awoke. The dust storms of Mars reshape our timelines for exploration, a planet that can still throw tantrums. During global dust storms, the surface of Mars becomes completely invisible from space, hidden beneath a swirling orange shroud. When a global dust storm reaches its peak intensity, spacecraft orbiting Mars look down upon a featureless sphere of orange-tan haze. The great volcanoes vanished, the canyons erased, the polar caps hidden beneath an atmosphere so choked with particles that nothing on the surface can be distinguished, as though the entire planet has drawn a curtain across itself and withdrawn from observation. Even instruments designed to see through atmosphere struggle during these events, their signals absorbed and scattered by the thick veil of suspended dust, and scientists must wait patiently for the storm to subside before resuming their studies of the surface below. The dust can take months to fully settle, drifting down grain by grain until the familiar rust-colored landscape emerges once more from beneath its temporary shroud. It is a reminder that Mars is not a static museum, but a world with moods and seasons, still capable of hiding from our gaze. The temperature on Mars can swing by over 100 degrees Celsius in a single day, from bitter cold at night to merely freezing at noon. The thin Martian atmosphere holds almost no capacity to trap heat, which means that as soon as the sun sets, the warmth accumulated during the day radiates away into space with startling speed, dropping temperatures from perhaps 10 degrees Celsius at noon to below -70 or even -100 degrees Celsius by midnight in some regions. This extreme daily variation places immense thermal stress on any equipment exposed to the surface, causing materials to expand and contract with each cycle, and it creates challenges for future human habitats that must somehow insulate against both the daytime warmth and the nighttime chill. The absence of oceans or thick air to buffer these swings means that every night on Mars is a plunge into deep cold, and every sunrise brings a slow climb back toward temperatures that still feel frigid by Earth standards. Day and night are different worlds there, the same sky holding both fire and ice. Fog and frost form on Mars in the early morning, thin layers of water ice that vanish as the sun rises. In the cold hours before Martian dawn, when temperatures reach their lowest point and the air is still, thin layers of frost can form on rocks and soil, delicate crystals of water, ice that condense from the tiny amount of moisture in the atmosphere and coat the landscape in a faint white dusting, only to vanish within minutes once the sun climbs above the horizon and begins to warm the surface. Rovers have photographed these frost layers glinting in the early light, ephemeral decorations that hint at the water cycle that still operates on Mars, however faintly compared to the rains and snowfalls of Earth. In some regions, particularly in valleys and crater floors where cold air pools overnight, fog has been observed clinging to the low ground, wisps of mist that fade as the morning advances and the air begins to warm and rise. These are fleeting moments of moisture on a dry world. A whisper of water in the pre-dawn stillness. And from the thin, dusty skies of Mars, We now turn to the giants that rise from its surface, the towering volcanic mountains that have stood silent for millions of years. Olympus Mons is the tallest known mountain in the solar system, rising nearly 22 kilometers above the surrounding plains. Rising from the dusty plains of the Tharsis region like a shield left by some ancient god, Olympus Mons towers nearly 22 kilometers above the surrounding terrain, more than 2.5 times the height of Mount Everest. Its summit so high that it pokes above most of the Martian atmosphere into a near vacuum where the stars are visible even at noon. This immense volcano accumulated its bulk over billions of years of eruptions, lava flowing down its gentle slopes and spreading outward in layer upon layer, building slowly because the crust beneath it never moved, never carried the volcano away from its magma source the way plate tectonics would have done on Earth. The caldera at its peak is a complex of overlapping craters formed by successive collapses, a sunken crown atop a mountain so vast that its true scale is difficult to grasp even with the best photographs. It is a monument to geological patience, a mountain built by time itself. The base of Olympus Mons is so wide that if you stood at its center, you could not see its edges because they would lie beyond the horizon. The footprint of Olympus Mons spans roughly 600 kilometers in diameter, an area comparable to the entire country of Italy, and the volcano's slopes are so gradual, rising at angles of only a few degrees, that if you stood at its center, you would see only a gentle rise stretching in every direction, the edges of the mountain lying well beyond the curve of the Martian horizon, invisible no matter how far you walked. This extraordinary breadth means that climbing the volcano would feel less like scaling a peak and more like walking across a gently tilted plain that never seems to end, the summit remaining distant even after days of travel, the landscape changing so subtly that progress would be hard to gauge. From orbit, the shape is clear, a broad circular bulge with radial ridges marking ancient lava flows, but from the surface, the scale would be almost impossible to comprehend, too vast for the eye to capture. A mountain that hides its own enormity. Olympus Mons is a shield volcano, built slowly over billions of years by countless eruptions of fluid lava. The gently sloping profile of Olympus Mons marks it as a shield volcano, a type formed by the repeated flow of highly fluid basaltic lava that travels long distances before cooling and solidifying, building a broad, rounded dome rather than the steep cone of more explosive volcanic mountains. On Earth, the Hawaiian volcanoes are shield volcanoes as well, built by similar processes, but the islands drift over the mantle hotspot that feeds them, creating a chain of progressively older peaks, while on Mars, the crust remains stationary and Olympus Mons has had billions of years to grow without interruption. Each eruption added another thin layer to the structure, lava spreading across acres and cooling into basalt, the entire mountain constructed from countless overlapping flows that accumulated into something almost unimaginably large. It is a record of patience written in stone, billions of years of slow volcanic breathing. The caldera at the summit of Olympus Mons is 80 kilometers wide, large enough to contain an entire city. At the summit of Olympus Mons lies not a single crater, but a complex of 6 overlapping calderas, collapse features formed when magma chambers below the surface drained and the rock above sank inward, creating a nested depression roughly 80 kilometers across and nearly 3 kilometers deep, large enough to contain a major metropolitan area with room to spare along its cliffs and terraces. These calderas record different episodes in the volcano's history, each collapse representing a moment when the mountain exhaled its molten interior and then sagged under its own weight. The youngest of them perhaps only a few 100 million years old, geologically recent by Martian standards. The floors of these craters are relatively smooth, filled with the last lava flows that pooled there before the eruptions ceased, their surfaces cracked and fractured by cooling and settling over time. A sunken crown atop the highest throne in the solar system, collapsed glory still magnificent. The cliffs surrounding the base of Olympus Mons drop 6 kilometers straight down, sheer walls of ancient volcanic rock. Around much of the perimeter of Olympus Mons runs a dramatic escarpment, a massive cliff face that drops as much as 6 kilometers from the edge of the volcano down to the surrounding plains, a vertical distance greater than any cliff on Earth, created by a combination of faulting, landslides, and the sheer weight of the volcanic pile pressing down on the crust beneath. These cliffs are so steep and so high that standing at their base you would feel as though you were at the foot of an endless wall rising toward the heavens, the top lost in the haze of dust and thin atmosphere, while from the top the plain below would seem impossibly distant, a different world entirely. The origin of these escarpments remains debated, perhaps formed by thrust faulting as the volcano's mass pushed outward, perhaps by catastrophic landslides, or perhaps by erosion at the interface between volcanic rock and less stable material beneath. The mountain declares its boundaries with walls of stone, a fortress built by nature. The Tharsis region of Mars contains 3 enormous volcanoes in a row, each one taller than Mount Everest. Stretching across the Tharsis rise in a nearly perfect diagonal line stand 3 massive shield volcanoes, Olympus Mons, Valles Mons, and Drowsy Mons, each one towering between 14 and 18 kilometers above the surrounding terrain, making every one of them taller than any mountain on Earth, their summits reaching into the thin upper atmosphere where the sky darkens toward the black of space. These 3 giants together form a volcanic province unlike anything elsewhere in the solar system, their alignment possibly reflecting deep fractures in the Martian crust through which magma rose over billions of years, or perhaps the track of a mantle plume that fed first one volcano and then the next. The shadows they cast at sunset stretch for hundreds of kilometers across the rust-colored plains, and their calderas, like that of Olympus Mons, record histories of eruption and collapse spanning epochs. They stand in silent procession, 3 sentinels watching over the Martian dusk. The Tharsis Bulge is a massive volcanic plateau that has warped the entire shape of Mars over billions of years. The Tharsis region is not simply a collection of volcanoes, but an immense plateau, a bulge in the Martian crust roughly 4,000 kilometers across and rising an average of 7 to 10 kilometers above the surrounding terrain, so massive that its weight has visibly deformed the planet, creating fractures, faults, and canyons radiating outward like cracks spreading from a heavy weight pressed onto a sphere. This bulge formed over billions of years as magma welled up from the Martian interior and accumulated on the surface, never dispersed by plate motion as it would have been on Earth, building a lopsided protrusion that shifted the planet's center of mass and may even have caused the poles to wander in the distant past. The Great Canyon system of Valles Marineris is thought to have formed as the crust cracked and stretched under the stress of Tharsis's weight, a scar created by the planet struggling to support what it had built, one region heavy enough to reshape a world, a burden carried for 4 billion years. Valles Mons is one of the largest volcanoes on Mars by area, stretching over 1,500 kilometers across. North of the main Tharsis group lies Valles Mons, a volcano so broad and so flat that it barely registers as a mountain when seen from orbit. Its slopes, rising at angles of less than 1 degree, spreading across more than 1,500 kilometers, an area larger than most European countries, yet reaching a height of only 6 or 7 kilometers above the surrounding plains. Unlike the more prominent shield volcanoes to the south, Olympus Mons grew outward rather than upward, its lavas spreading thin across an enormous footprint before cooling, building a structure that could hold millions of square kilometers under its gentle dome. Its caldera is relatively small and shallow compared to those of its neighbors, but the sheer extent of its base speaks to eruptions that occurred across eons, patient outpourings of melt that turned a region into a gently bulging swell of volcanic rock. Not tall, but impossibly wide, a volcano measured in horizons rather than heights. The volcanoes of Mars are thought to be dormant rather than extinct, and some may have erupted within the last few million years. Although no active eruption has ever been observed on Mars, recent analysis of lava flows suggests that some Martian volcanoes may have erupted within the last few million years, a blink of an eye in geological time, which raises the tantalizing possibility that the planet's volcanic engines are merely sleeping rather than permanently cold. Lava flows on the flanks of Olympus Mons and in the Elysium region show remarkably fresh surfaces, with few impact craters to mark the passage of time, implying ages measured in millions rather than billions of years. If magma still exists somewhere beneath the Martian crust, perhaps pooling in chambers that have not yet found pathways to the surface, then the volcanoes may someday stir again, and the red planet could once more experience the fiery birth of new rock from deep within its interior. The fires may have dimmed but not gone out, a planet that might yet remember how to breathe smoke. Because Mars lacks plate tectonics, its volcanoes can grow to enormous sizes, fed by the same magma source for billions of years. On Earth, the constant movement of tectonic plates carries volcanoes away from the hotspots that feed them, creating chains of progressively older mountains like the Hawaiian Islands, where each volcano has only a few million years to grow before being carried away from its source of magma. Mars has no such mechanism, its crust a single unmoving shell, and this means that when a hot spot or plume of molten rock rises from the interior, it stays beneath the same spot for billions of years, feeding eruption after eruption into the same vent, allowing a single volcano to accumulate mass on a scale impossible anywhere on our restless Earth. This is why Olympus Mons could grow to be the tallest mountain in the solar system, why the Tharsis volcanoes stand like giants, while Earth's volcanoes are scattered and modest. A still crust beneath a patient fire, mountains that had eternity to rise. And from these sleeping giants of fire and stone, we descend now into the deepest scar on the Martian surface, a canyon system that stretches across the face of a world. Valles Marineris is the largest canyon system in the solar system, stretching over 4,000 kilometers across Mars. Carved into the rust-colored crust of Mars like a wound that never healed, Valles Marineris stretches over 4,000 kilometers from east to west, a distance comparable to the width of Australia or the journey from Lisbon to Moscow, making it by far the largest canyon system ever discovered in our solar system. If placed upon Earth, this immense gash would span the entire continental United States, its walls rising above the clouds, its depths plunging into perpetual shadow where sunlight reaches only at noon. The canyon is not a single chasm, but a complex of parallel troughs, interconnecting valleys, and chaotic collapsed terrain, all carved and shaped by processes that continue to puzzle scientists decades after the first spacecraft photographed them. It is a feature so immense that its full extent is only truly visible from orbit, a scar written across the face of a world. In some places, Valles Marineris plunges 7 kilometers deep, more than 4 times deeper than the Grand Canyon. The walls of Valles Marineris drop as much as 7 kilometers from rim to floor in some sections, a vertical distance so great that the Grand Canyon of Arizona could fit inside with room to spare, plunging to depths where the air pressure is noticeably higher than on the surrounding plains, and where the shadows linger long after sunrise has brightened the plateau above. Standing at the bottom of such a canyon, you would be surrounded by walls rising to heights that dwarf any mountain on Earth, their layers recording billions of years of Martian geological history, exposed by whatever forces tore this great gash in the planet's skin. Light would reach the floor only briefly at midday, the rest of the time spent in a twilight that deepens to utter darkness after sunset, a world within a world hidden beneath the familiar red surface, too deep for human eyes to fully grasp. A chasm measured in kilometers of shadow. If Valles Marineris were on Earth, it would stretch from the Atlantic coast of Europe to the shores of the Mediterranean. The scale of Valles Marineris is so immense that placing it upon a globe of Earth would see its western end beginning somewhere near Portugal and its eastern terminus reaching past Turkey to the shores of the Mediterranean. A single geological feature spanning an entire continent, crossing mountain ranges and river valleys and political borders as though they were nothing. A reminder that planetary scales operate on dimensions that human geography cannot contain. Entire nations would fit within its walls, their cities nestled on the floor of a canyon 6 times deeper than any on our own world, the rim above them lost in haze and distance. This comparison helps bridge the gap between photographs taken by orbiting spacecraft and the lived experience of someone standing on Martian soil, confronting a landscape whose proportions exceed anything in our direct experience. A feature larger than civilizations, geography on a scale that humbles comprehension. Scientists believe Valles Marineris formed as the Tharsis bulge rose, cracking the Martian crust like a shell. The origin of Valles Marineris is closely tied to the enormous volcanic province of Tharsis that lies just to its west. For as that great bulge of volcanic material accumulated over billions of years, its weight pushed down on the crust and caused the surrounding regions to stretch and warp, fracturing along lines of weakness and eventually tearing open the gigantic rift that we see today. Unlike the Grand Canyon, which was carved primarily by running water cutting through rock, Valles Marineris appears to have begun as a tectonic feature, a crack in a stressed shell that then widened through collapse, landslides, and perhaps later erosion by water or ice. The relationship between the bulge and the canyon is visible even from orbit, the canyon radiating outward from Tharsis like a crack spreading from a heavy weight. The planet split under its own burden, a wound opened by the weight of volcanoes. Ancient water may have once flowed through Valles Marineris, carving channels and depositing sediments on the canyon floor. While the initial formation of Valles Marineris was tectonic rather than erosional, there is compelling evidence that water later flowed through portions of the canyon system, carving subsidiary channels into the walls, depositing layered sediments on the floor, and perhaps even pooling into lakes that persisted for millennia before evaporating or freezing away. Minerals detected from orbit, including clays and sulfates that form in the presence of water, support the idea that liquid once interacted with the rocks within these depths, altering their chemistry and leaving behind signatures that spacecraft instruments can read from hundreds of kilometers above. If water indeed flowed here, then Valles Marineris may have been one of the last refuges of liquid on Mars, protected from the thinning atmosphere by its depth and possibly fed by underground sources. Rivers in a canyon that now holds only dust. a memory of flowing water carved in stone. Rest here for a moment in the shadow of these ancient canyons. Let the stillness of Mars settle into your mind and feel the weight of your body pressing gently into wherever you are resting. There is no rush. The canyons have waited for billions of years. And from the depths of Valles Marineris, we now follow the traces of something precious, something that may have once flowed freely across the Martian surface: water. Billions of years ago, Mars had rivers, lakes, and possibly even an ocean covering much of its northern hemisphere. The Mars we see today, dry and dusty and cold, was not always so barren. For billions of years ago, the planet bore a thicker atmosphere, warmer temperatures, and abundant liquid water that carved river valleys into its surface, filled crater basins with lakes, and may even have formed a vast ocean covering much of the northern lowlands, an expanse of water that might have lapped against shores where now only rust-colored desert stretches to the horizon. Evidence for this wetter past comes from spacecraft observations that reveal ancient river channels, lake beds lined with sedimentary deposits, and mineral formations that could only have occurred in the presence of standing water over extended periods. What transformed Mars from that warmer, wetter world into the frozen desert of today remains one of the great questions of planetary science, but the evidence is clear that water once flowed here in quantities rivaling or exceeding what we see on Earth. A world that once knew rain and rivers, now it dreams of oceans. Dried river valleys on Mars stretch for hundreds of kilometers, winding channels carved by water that vanished long ago. Across the ancient highlands of Mars wind numerous dried river valleys, channels that meander and branch in patterns instantly recognizable to anyone who has flown over Earth and looked down at river systems cutting through landscapes. Evidence that liquid water once flowed here in sufficient volumes to carve stone, to erode banks, to create tributaries and deltas, and all the features we associate with flowing water on our own planet. Some of these valleys stretch for hundreds of kilometers, their courses still visible despite billions of years of dust accumulation and meteorite bombardment, testaments to times when rain may have fallen on Martian soil and collected into streams that carried sediment toward vast lowland basins. The water that carved them is long gone, evaporated or frozen or escaped to space, leaving behind only these dry traces etched into rock that remembers what once passed through. Riverbeds without rivers. Stories written in the shape of valleys. Gale Crater, where the Curiosity rover landed, was once filled with a lake that persisted for millions of years. The landing site of the Curiosity rover, Gale Crater, was chosen in part because the sedimentary layers visible in Mount Sharp at its center suggested a complex history involving water. And sure enough, the rover has found compelling evidence that the crater once held a lake that may have persisted for millions of years, filling and draining in cycles as the Martian climate shifted, depositing layer upon layer of sediment that lithified into rock, now exposed on the mountainside. These lake sediments contain clays and other minerals that form only in the presence of water with chemistry that could have supported microbial life, making Gale Crater one of the most promising places to search for evidence that Mars was once habitable. The rover has driven across what were once lake beds, sampled rocks that were deposited in shallow water, and photographed features that tell of a time when this now dry crater was a basin of liquid, a lake that remembers its own existence, waiting for someone to read its story. The North Polar ice cap of Mars contains enough water ice to fill a lake several meters deep across the entire planet. At the North Pole of Mars lies a layered deposit of ice and dust that measures roughly 1,000 kilometers across, a gleaming white cap visible from orbit, composed primarily of water ice mixed with dust and frozen carbon dioxide, in a structure that holds enough frozen water to cover the entire Martian surface in a layer several meters deep if it were melted and spread evenly. These ice deposits record thousands of cycles of Martian climate, each layer representing a season or group of seasons when dust or ice accumulated in slightly different proportions, creating a frozen archive of planetary history that scientists hope to someday read in detail. During summer, the outer edges of the cap sublimate, shrinking the visible white region as carbon dioxide ice returns to the atmosphere, while the permanent core of water ice remains year-round, too cold to melt or sublimate under current conditions. A frozen archive of climate written in layers, water waiting beneath the polar sky. The South Polar ice cap includes a mix of water ice and frozen carbon dioxide, creating layers that record climate history. The southern polar cap of Mars presents a more complex picture than its northern counterpart, with a seasonal layer of carbon dioxide frost that expands dramatically during winter and shrinks during summer, overlying a permanent cap of mixed water ice and carbon dioxide that may extend to significant depths beneath the surface. This layering creates a striped appearance in detailed images, bright bands of nearly pure ice alternating with darker bands where dust has been incorporated, a record of seasonal and longer-term climate variations stretching back perhaps millions of years. The South Pole is also home to some of the strangest terrain on Mars, including the so-called Swiss cheese features, where pits in the carbon dioxide ice create otherworldly patterns that shift and change with each passing year. Ice stacked like pages of history, a polar library written in frost. Beneath the surface of Mars, scientists have detected vast reservoirs of ice buried under dust and rock. Below the red dust that covers so much of Mars lies ice, not just at the poles, but across wide swaths of the mid-latitudes, buried beneath layers of regolith that insulate it from the warmth of the sun and keep it frozen despite the occasional warmth of Martian summer. Radar instruments orbiting Mars have detected these subsurface deposits, bright reflections indicating vast reservoirs of water ice resting in the shallow subsurface, resources that could someday support human settlements if they can be extracted and melted. Some of this ice is ancient, dating back to periods when the Martian climate was different, while some may have formed more recently as water vapor in the atmosphere migrated to colder regions and condensed. The red surface hides what lies beneath, a planet that has stored its water underground. Some slopes on Mars show dark streaks that grow and fade with the seasons, possibly caused by briny water seeping to the surface. On sun-facing slopes across the warmer regions of Mars, spacecraft have observed dark streaks that appear during the warm season and fade as temperatures cool, features called recurring slope lineae that some scientists believe might be caused by briny water seeping to the surface, liquid enough to flow briefly before evaporating in the thin air. If these streaks are indeed caused by liquid water, even water so salty that it remains liquid at temperatures far below the freezing point of pure water, then Mars may not be entirely dead from a hydrological perspective, and there could be places where moisture occasionally stirs in the soil. However, the evidence remains controversial, with some researchers arguing that dry granular flows could create similar features without any liquid water at all, and the question remains open. Dark lines that come and go, perhaps the pulse of water in a nearly dry world. Mars lost most of its water over billions of years as the atmosphere thinned and solar wind stripped away molecules into space. The transformation of Mars from a wet world to a frozen desert took billions of years and involved the slow escape of atmospheric molecules into space, particularly after the planet lost its protective magnetic field and became exposed to the relentless stream of charged particles from the sun that stripped away gases atom by atom. As the atmosphere thinned, the pressure dropped and temperatures fell, and water that had once flowed freely began to freeze, some of it locked into the poles and subsurface, some of it broken apart by ultraviolet light, and its hydrogen lost to space forever. This process continues even today, with spacecraft measuring the ongoing escape of what little atmosphere remains, a slow exhalation that will continue for billions more years. The water did not vanish all at once. It drifted away, particle by particle, across eons. If all the known ice on Mars melted, it could potentially cover the planet in a shallow ocean tens of meters deep. Estimates of the total water ice remaining on Mars, counting the polar caps, the subsurface deposits, and ice trapped in crater shadows and high-altitude regions, suggest that if it were all melted and spread evenly across the planetary surface, the resulting ocean would be tens of meters deep, perhaps as much as 35 meters in some calculations, enough to be a substantial body of water, though far less than what Earth's oceans hold. This ice represents what remains of a once much larger inventory, the portion that did not escape to space or react chemically with the rocks, frozen remnants of a hydrological cycle that once may have rivaled Earth's in its youth. For future explorers, this ice represents a crucial resource, potential drinking water, rocket fuel, and irrigation for greenhouses, all locked beneath the dust awaiting extraction. Water enough for an outpost, perhaps the foundation for something more. Hydrated minerals found on Mars provide evidence that water interacted with rock for extended periods in the distant past. Across the Martian surface, spacecraft instruments have detected a variety of hydrated minerals, compounds that incorporate water molecules into their crystal structure and form only when liquid water remains in contact with rock for extended periods, evidence not of brief floods or transient moisture, but of sustained wet environments where chemistry had time to alter the planet's geology in lasting ways. Clays, sulfates, and other hydrated minerals appear in layered deposits, in the walls of craters, and in ancient delta fans, each occurrence a marker of conditions that were once far more hospitable than what we see today. These minerals are targeted by rovers searching for signs of past habitability, because the chemistry that created them might also have supported simple life forms, if any ever arose on Mars. Water stayed long enough to change the rocks, long enough perhaps for life to take hold. And from the ancient waterways and frozen reservoirs of Mars, we now turn to an invisible force, or rather, the absence of one, the lost magnetic field that once shielded this world. Mars once had a global magnetic field like Earth's, but it faded away billions of years ago. In its youth, Mars generated a global magnetic field much like Earth does today, powered by convection currents in its liquid iron core, a protective bubble that shielded the surface from the solar wind and helped keep the atmosphere intact. But this field weakened and died sometime in the first billion years of the planet's existence, leaving Mars exposed to the relentless bombardment of charged particles from the sun. The exact cause of this magnetic death is still debated, but it likely relates to the cooling of the Martian interior, a smaller planet losing its internal heat more quickly than Earth and seeing its core solidify before the protective dynamo could be sustained. Once the field was gone, the atmosphere began its slow escape into space, setting in motion the transformation of Mars from a potentially habitable world to the cold desert we see today, a shield that failed, a world left unprotected. Without a magnetic field, Mars has no protection from the solar wind, which slowly strips away its atmosphere. The solar wind is a constant stream of charged particles flowing outward from the sun, energetic enough to knock atoms out of any atmosphere not protected by a magnetic field. And on Mars, This process has been stripping away gases for billions of years, slowly eroding what was once a thicker atmospheric blanket into the thin wisp that remains today. Spacecraft have measured this ongoing loss directly, watching oxygen and hydrogen atoms drift away from the upper atmosphere and disappear into the void of space, a trickle that over geological time adds up to an enormous volume of lost air. Earth's magnetic field deflects most of these particles, channeling them toward the poles where they create the auroras, but Mars has no such shield, and every day more of its atmosphere vanishes forever, a planet slowly exhaling into space. The breath of a world drifting away. Patches of ancient magnetized rock still exist on the Martian surface, remnants of the planet's former magnetic shield. While Mars no longer possesses a global magnetic field, spacecraft have detected patches of strongly magnetized rock in the ancient southern highlands, crustal remnants from the era when the planetary dynamo was still active, frozen into stone billions of years ago and preserved ever since as localized magnetic anomalies scattered across the surface. These patches appear in roughly parallel stripes in some regions, patterns that have led some scientists to speculate that Mars may have briefly experienced something like the magnetic reversals and seafloor spreading seen on Earth, though the evidence remains debated and the full story is unclear. What is certain is that these magnetized rocks are among the strongest crustal magnetic fields in the solar system, far stronger than anything found on Earth's surface, echoes of a time when Mars was a more dynamic world, fossils of a lost magnetic heart, ancient strength frozen into stone. The loss of the magnetic field is one of the main reasons Mars transformed from a warm, wet world to the cold desert it is today. When Mars lost its magnetic field, the solar wind began stripping away the atmosphere, and as the atmosphere thinned, the planet lost its ability to trap heat, temperatures dropped, and the water that had once flowed freely began to freeze and evaporate, setting in motion a cascade of changes that transformed a world that might have supported life into the cold, dry desert we see today. This chain of events is thought to have unfolded over hundreds of millions of years, a gradual decline rather than a sudden catastrophe, but the end result was the same, a planet frozen in a state of suspended animation, its water locked in ice, its surface scoured by ultraviolet radiation, its skies emptied of the thick air that once held warmth. The magnetic field was the first domino, everything else followed from its fall. Radiation levels on the Martian surface are significantly higher than on Earth, posing a challenge for future human explorers. Without a thick atmosphere or magnetic field to deflect or absorb incoming radiation, the surface of Mars receives a constant bombardment of cosmic rays and solar particles that would pose serious health risks to any human beings living there unprotected, raising the lifetime risk of cancer and potentially causing other long-term damage to the body. The radiation dose on Mars is roughly 2 to 3 times what astronauts experience on the International Space Station, which itself is shielded by Earth's magnetic field, and it increases dramatically during solar storms when bursts of energetic particles race outward from the Sun. Future Martian settlers will need to shield their habitats with soil, rock, or other materials, and may need to spend significant time underground or in heavily protected structures. Living on Mars will mean living carefully. The sky offers beauty, but also danger. The thin Martian atmosphere provides almost no protection from cosmic rays or solar radiation. Earth's atmosphere acts as an effective shield against most cosmic radiation, the column of air above any given point equivalent to about 10 meters of water in its ability to stop energetic particles. But the thin atmosphere of Mars provides only a fraction of this protection, allowing cosmic rays to reach the surface with relatively little attenuation, a hazard that would be present every moment of every day for anyone living there. During solar flares, when the sun emits bursts of particularly energetic particles, the radiation levels on Mars can spike dramatically, potentially delivering dangerous doses to anyone caught outside a shielded habitat. Even ordinary cosmic rays, the constant background arriving from distant supernova remnants and other sources throughout the galaxy, penetrate easily to the surface. The thin air that makes the sky pink also makes the world less safe. A veil that is nearly transparent to danger. Scientists theorize that Mars may have had a magnetic field for only the first billion years of its existence. Based on the dating of magnetized rocks in the southern highlands and the absence of magnetization in younger volcanic formations, scientists estimate that the Martian magnetic field shut down roughly 4 billion years ago, meaning that for most of the planet's history, there has been no global shield, no protection from the solar wind, no help in keeping the atmosphere intact. The Martian dynamo may have operated for only the first fraction of the planet's existence, a window of protection that closed before life, if it ever arose, had time to become firmly established. Earth's dynamo, by contrast, has been running for at least 3.5 billion years and shows no signs of stopping, a difference that may ultimately explain why one planet teems with life while the other appears silent. A brief magnetic youth, then 4 billion years of exposure. The core of Mars is thought to be partially liquid, but it no longer generates a dynamo strong enough to create a magnetic field. Although recent seismic data from the InSight lander suggests that the core of Mars may still be at least partially liquid, the convection currents that once drove the planetary dynamo have apparently ceased, the interior too cool or too sluggish to maintain the fluid motions necessary for generating a global magnetic field. The precise state of the Martian core remains a subject of active research, with instruments listening for seismic waves that bounce off and through the iron-rich interior, gradually building a picture of a planet that has grown still and cold at its center. If the core is indeed liquid, it is the quiet kind of liquid, barely stirring, its once vigorous currents faded to whispers too faint to magnetize the world above. A heart that still flows but no longer beats. Iron slowing to silence. Some researchers have proposed creating an artificial magnetic shield to help terraform Mars in the distant future. Looking far into a hypothetical future, when humans might attempt to transform Mars into a world more habitable for Earth life, some researchers have proposed launching an artificial magnetic shield to the gravitational balance point between Mars and the Sun, generating a protective field that would deflect the solar wind and allow the atmosphere to gradually thicken over centuries or millennia. Such a shield would not need to replicate the strength of Earth's magnetic field, merely enough to reduce the atmospheric losses to a rate slower than volcanic or comet-delivered replenishment, and the technology required, while far beyond what we can deploy today, is not in principle impossible. Whether humanity will ever have the resources, motivation, and patience to undertake such a project remains entirely speculative. A dream of rebuilding a shield, engineering on a planetary scale. Despite the harsh radiation, some extremophile microbes on Earth could potentially survive beneath the Martian surface. Laboratory experiments have subjected various hardy microorganisms from Earth to simulated Martian conditions, including the intense ultraviolet radiation, the extreme cold, and the desiccating dryness, and found that while the surface would quickly kill most life, certain extremophile organisms could survive if shielded by just a few centimeters of soil, protected from radiation in the subsurface, where temperatures remain more stable and ice may still exist. This raises the tantalizing possibility that if life ever arose on Mars during its warmer, wetter youth, it might have retreated underground as conditions worsened, finding refuge in the aquifers and pockets of moisture that may persist beneath the frozen surface. Whether anything actually survives there today remains one of the greatest unanswered questions in planetary science. The surface is hostile, but the depths might harbor secrets. And from the invisible forces that once protected Mars, we now lift our gaze to the night sky, where two small, misshapen moons circle the red planet in silence. Mars has two moons, Phobos and Deimos, both named after the Greek gods of fear and terror. Circling Mars in swift, silent orbits are two small moons, Phobos and Deimos, named after the mythological sons of Ares who accompanied their father into battle, Phobos representing fear and Deimos representing terror, companions to the god of war, just as these tiny worlds are companions to the planet that bears his Roman name. Both moons are small, dark, and irregular, looking more like captured asteroids than the rounded spheres of larger moons, their surfaces pitted with craters and grooved with strange fractures that hint at violent histories. They were discovered within a few days of each other in 1877 by American astronomer Asaph Hall, who nearly gave up his search before his wife encouraged him to continue, and their presence has fascinated scientists ever since, raising questions about how they came to orbit Mars and what their ultimate fate may be. Two small attendants to a red world, fear and terror circling in the dark. Phobos is the larger of the two moons, a lumpy, potato-shaped rock only 22 kilometers across. The inner and larger of Mars's two moons, Phobos measures roughly 22 kilometers at its widest, a lumpy, dark mass that resembles a potato more than the spherical moons we are accustomed to seeing, its gravity too weak to pull itself into a round shape, leaving it as an irregular chunk of rock scarred by impacts and marked by a single enormous crater that dominates one side. Its surface is covered in a thick layer of regolith, dusty debris accumulated from billions of years of small impacts, and its color is among the darkest of any body in the solar system, reflecting only a fraction of the sunlight that strikes it. Despite its small size, Phobos looms large in the Martian sky because it orbits so close to the planet, racing around Mars more than 3 times every day. A swift companion, a dark shape flying through the Martian night. Deimos is even smaller than Phobos, measuring just 12 kilometers across, one of the smallest moons in the solar system. The outer moon, Deimos, is barely 12 kilometers across at its widest, so small that standing on its surface, you would have trouble perceiving any horizon at all, the ground curving away rapidly in every direction, and you could walk completely around it in a few hours if you did not float away with each step in its almost negligible gravity. Like Phobos, Deimos is irregularly shaped, dark, and heavily cratered, though its craters are filled with thick regolith that gives its surface a smoother appearance than its larger sibling. It orbits much farther from Mars than Phobos does, taking more than 30 hours to complete each journey around the planet, and from the Martian surface, it would appear as a bright but tiny point of light, barely distinguishable from a star at first glance, one of the smallest moons we know, yet circling faithfully where it has always been. Phobos orbits so close to Mars that it rises and sets twice in a single Martian day. So close does Phobos orbit to Mars that it circles the planet faster than Mars itself rotates, completing each orbit in just under 8 hours, which means that from the Martian surface you would see it rise in the west and set in the east, the opposite direction from the sun and from every other object in the sky, appearing twice above the horizon during a single sol. This rapid transit makes Phobos one of the fastest moving objects visible in any planetary sky, racing among the stars in a way that would seem almost urgent to anyone watching from below. The moon is so close, in fact, that someone standing at the Martian poles would never see it at all, the curvature of the planet blocking it from view, an inner moon that refuses to slow down, chasing its own shadow around the world. In about 50 million years, Phobos will either crash into Mars or break apart to form a ring around the planet. The orbit of Phobos is not stable over geological timescales, for tidal forces are slowly pulling the moon closer to Mars with each passing century, shrinking its orbit by a few centimeters per year, a process that will eventually bring it so close that either the moon will plunge into the Martian surface, or more likely, the gravitational stresses will tear it apart and spread its remains into a ring of debris encircling the planet. Scientists estimate this catastrophic end will occur in roughly 50 million years, a blink of an eye for a planet that has existed for more than 4 billion. But for now, Phobos continues its swift journeys, apparently unaware of the fate that awaits it. The fragments of such a ring would eventually rain down onto Mars, slowly clearing the sky of their debris, a moon living on borrowed time, spiraling slowly toward destruction. Let these quiet moons drift through your thoughts now, circling gently as you rest. There is nothing to hold on to, nothing to figure out. Just let the stillness carry you, like Phobos and Deimos circling endlessly through the Martian night. Deimos orbits much farther from Mars and moves so slowly across the sky that it stays above the horizon for nearly 3 days at a time. In contrast to the swift passage of Phobos, Deimos hangs in the Martian sky for far longer, its distant orbit keeping it above the horizon for nearly 3 Earth days at a time from many locations on the surface, drifting slowly from east to west like a dim star that crawls across the heavens so gradually that you might forget it was moving at all. Its orbital period is longer than a Martian day, which means it rises in the east like the sun and other stars, but so slowly that it seems almost frozen in place, a stationary point of light in the pink evening sky. Watching Deimos would require patience, for it moves so imperceptibly that changes in position would be noticed only over hours, a moon that seems to be waiting for something, the slow companion, patient and unhurried in its distant path. Both moons are thought to be captured asteroids, pulled into orbit around Mars billions of years ago. The dark colors, irregular shapes, and compositions of Phobos and Deimos strongly resemble those of certain classes of asteroids found in the outer asteroid belt, leading many scientists to believe that these moons are captured objects, wanderers from the belt of rocky debris between Mars and Jupiter that strayed too close to the red planet billions of years ago and were seized by its gravity. How exactly they were captured remains uncertain, since the physics of capturing an asteroid into a stable orbit is surprisingly difficult without some mechanism to remove energy, perhaps a denser early atmosphere that could have slowed them, or perhaps collisions or gravitational interactions we do not yet fully understand. Whatever their origin, they are now bound to Mars forever. Strangers who became companions, adopted into the Martian family long ago. Phobos has a giant crater called Stickney that covers nearly half of its entire surface. Dominating one hemisphere of Phobos is Stickney crater, an impact scar nearly 10 kilometers across, so large relative to the moon's overall size that the collision which created it must have come within a breath of shattering Phobos entirely. Cracks radiating outward from the crater rim across the small moon's surface, like fractures in an eggshell struck too hard. The crater is named after Chloe Angeline Stickney Hall, the wife of the astronomer who discovered both Martian moons, a tribute to the woman who encouraged him to continue searching when he was ready to give up. Inside the crater, terraced walls reveal the interior structure of Phobos, layers of material compressed by billions of years of smaller impacts. a wound that nearly killed its world, a reminder of violence still visible today. The grooves across the surface of Phobos may be caused by tidal stresses slowly tearing the moon apart. Crisscrossing the surface of Phobos are series of parallel grooves, shallow troughs running for kilometers across the dark regolith, features that have puzzled scientists since they were first photographed, with explanations ranging from chains of impact craters to fractures formed during the Stickney impact to evidence that tidal forces from Mars are slowly pulling the moon apart even now. Recent analysis favors the tidal stress hypothesis, suggesting that as Phobos spirals closer to Mars, its structure is being strained by the increasing difference in gravitational pull between its near and far sides, stretching and fracturing the rock in patterns that trace across its surface like cracks in ice. If this interpretation is correct, then Phobos is already in the process of coming apart. The grooves are not merely scars from the past. They may be the writing of the moon's future destruction. From the surface of Mars, Phobos would appear about 1/3 the size of Earth's moon in our sky. Despite being far smaller than the moon as seen from Earth, Phobos's proximity to Mars means it appears reasonably large in the Martian sky, roughly 1/3 the diameter of our moon as we see it at home, large enough to show a visible disk rather than a mere point of light, large enough to cast shadows during the day as it transits across the face of the sun. Deimos, by contrast, appears so small that it looks almost star-like, a bright point that moves slowly across the sky without the obvious disk shape of its larger sibling. Solar eclipses on Mars are brief and partial, the small moons not quite large enough to fully cover the sun, but they are frequent, happening many times throughout the Martian year. A small moon, yet still a presence in the sky. And from the small moons that circle Mars, we now journey back through time to the long history of humanity watching the red wanderer cross our night sky. Ancient Egyptians called Mars the Red Horus, associating its color with the falcon-headed god of the sky. Long before telescopes or spacecraft, the ancient Egyptians watched the Red Wanderer move through the constellations, naming it Her-Desher, the Red One, and associating it with Horus, the falcon-headed god of the sky, kingship, and war, a connection drawn from its blood-red color and its backward motion through the zodiac that seemed to signal portents and divine messages. The Egyptians, the planets were living souls crossing the heavens, and Mars, with its distinctive color, visible even to the naked eye as unmistakably different from the steady white or yellow stars, held special significance as a celestial omen. Its appearances and disappearances, its retrograde loops across the night sky, were carefully tracked and recorded, part of a tradition of skywatching that stretched back thousands of years before the pyramids were built. Humanity has always noticed this red light, always wondered what it meant. The Babylonians named Mars after Nergal, their god of war and pestilence, recognizing its blood-red glow. In ancient Mesopotamia, the Babylonians identified the red planet with Nergal, their deity of war, plague, and the underworld, a god whose associations with destruction and conflict found a natural symbol in a wandering light, the color of blood drifting among the calm white stars. Babylonian astronomers kept meticulous records of planetary positions over centuries, tracking the movements of Mars with a precision that would not be surpassed until the work of Tycho Brahe and Johannes Kepler more than 2,000 years later, developing mathematical systems to predict when the planet would appear and where it would be in the sky. This tradition of careful observation laid the groundwork for all later astronomy, transforming the heavens from a realm of mystery into a domain of patterns and predictability. They watched the red star and found order in its wandering. The Romans named the planet after Mars, their god of war, a name that has endured for 2,000 years. When the Romans adopted the Greek tradition of associating planets with gods, they gave the Red Wanderer the name of their own war god, Mars, the father of Romulus and Remus, and the divine protector of Rome itself, a figure less chaotic than his Greek counterpart Ares, and more closely tied to agricultural guardian and civic honor before his martial nature came to dominate his mythology. The name has persisted for over 2,000 years, outlasting the empire that bestowed it, surviving the fall of classical civilization and the rise of the modern scientific tradition, remaining even now the only name by which this world is commonly known. We speak of Mars without thinking of ancient Rome, yet the name carries millennia of human imagination within it, a god's name, still echoing from antiquity. In the 17th century, astronomers first observed the polar ice caps of Mars through early telescopes. When astronomers first turned their primitive telescopes toward Mars in the 1600s, they began to notice features that hinted at a world with geography, not just a point of light, but a disk with light and dark markings. And among the most striking were bright patches at the poles that waxed and waned with the Martian seasons, unmistakable signs that something was changing on this distant world. Christian Huygens made some of the earliest detailed observations, sketching features that would later be mapped in greater detail, and Giovanni Cassini measured the planet's rotation period to within a few minutes of the modern value. These ice caps were immediately suggestive of Earth's own poles and sparked centuries of speculation about whether Mars might harbor conditions suitable for life, the first hints of a familiar world, ice glimpsed through shaky lenses. In 1877, astronomer Asaph Hall discovered both Phobos and Deimos within a single week. During the favorable opposition of 1877, when Mars passed closer to Earth than it had in years, American astronomer Asaph Hall used the Large Refractor Telescope at the United States Naval Observatory to search for any moons that might orbit the red planet. And on a single week in August, he found both, spotting first the outer moon Deimos, and then, 6 days later, the inner moon Phobos hidden in the glare of the planet itself. Hall had nearly abandoned the search before his wife, Angeline, encouraged him to continue, and his persistence was rewarded with a discovery that doubled the known moons of Mars in a matter of days. He named them after the mythological attendants of the god of war, fear, and terror, accompanying their divine master into battle. 2 moons found in 1 week, patience rewarded by the sky. And from centuries of watching Mars through telescopes, we now follow the spacecraft that made the journey across the void, landing on the red planet itself. The first successful flyby of Mars was achieved by Mariner 4 in 1965, revealing a cratered and barren world. After several failed attempts by both American and Soviet spacecraft, Mariner 4 became the first mission to successfully fly past Mars in July of 1965, sending back 22 grainy black and white photographs that shattered romantic visions of canals and dying civilizations, revealing instead a heavily cratered surface that looked more like the moon than the verdant world science fiction had imagined. These images showed a Mars that appeared ancient and dead, pummeled by impacts, with no trace of the vast engineering works that some had believed might exist there, and the scientific community began the slow process of adjusting its expectations about what we might find on this neighboring world. The data was crude by modern standards, but it was a beginning, the first close look, the first reckoning with reality. The Viking landers touched down on Mars in 1976 and were the first to send photographs from the Martian surface. In the summer and autumn of 1976, the 2 Viking landers descended through the thin Martian atmosphere and touched down on the surface, becoming the first spacecraft to successfully land on Mars and operate for an extended period, their cameras capturing the first color photographs ever taken from the ground of another planet. Images of a rocky, rust-colored desert stretching to a pink sky that millions of people on Earth stared at in wonder. These landers were equipped with robotic arms that scooped soil samples, weather stations that measured temperature and wind, and experiments designed to search for signs of life, ambitious missions that pushed the boundaries of what space exploration could accomplish. They operated for years, far exceeding their expected lifetimes. Our first eyes on the ground, looking back at Earth from Martian soil. Viking conducted experiments to search for life on Mars, but the results were ambiguous and still debated today. Among the most eagerly anticipated aspects of the Viking missions were 3 biology experiments designed to detect signs of life in the Martian soil, mixing samples with nutrients and searching for gases that might indicate metabolic activity. But the results that came back were puzzling and controversial, with one experiment returning positive signals that some scientists interpreted as evidence of life, while others attributed them to unusual chemical reactions involving the perchlorate-rich soil. Nearly 50 years later, the debate continues, with most researchers believing the results were caused by inorganic chemistry rather than biology, but a minority still arguing that we may have detected something unexpected and never followed up properly. The ambiguity has haunted Martian exploration ever since, a question asked but not answered, a mystery left hanging. The Pathfinder mission in 1997 delivered Sojourner, the first rover to explore the Martian surface. After 2 decades without a Mars landing, the Pathfinder mission arrived on the 4th of July 1997, bouncing to a stop in Ares Valles and deploying a small rover named Sojourner, the first wheeled vehicle ever to drive across the surface of another planet, no larger than a microwave oven, yet carrying cameras and instruments that examined nearby rocks and sent the data back to an audience of millions following online. Sojourner explored for nearly 3 months, traveling just over 100 meters in total, a modest distance by later standards, but an immense achievement for its time, demonstrating that rovers could operate successfully on Mars and paving the way for the larger and more capable vehicles that would follow. A small rover that opened a new era, the first wheels to roll on Martian dust. Spirit and Opportunity landed on Mars in 2004, designed to last 90 days, but surviving for years. In January of 2004, 2 identical rovers named Spirit and Opportunity landed on opposite sides of Mars, each designed for a primary mission of just 90 days, enough time to examine their immediate surroundings and search for evidence that water had once been present on the surface. But both far exceeded those expectations, Spirit operating for over 6 years and Opportunity continuing for nearly 15, an endurance that astonished even their designers. These rovers transformed our understanding of Mars, finding unmistakable evidence of ancient water in the form of mineral deposits, rock textures, and layered sediments that could only have formed in wet environments, proving that the red planet had once been far more hospitable than the frozen desert it is today. They became beloved characters in their own story, robots that refused to stop. Opportunity traveled over 45 kilometers across Mars, more than any other off-Earth vehicle in history at the time. Over the course of its nearly 15-year mission, the Opportunity rover traversed more than 45 kilometers of Martian terrain, rolling across plains and into craters, and along the rims of ancient impact basins, setting a record for the longest distance traveled by any vehicle on another world. A journey that would take a human, perhaps a day's walk, but that the patient rover spread across thousands of days of careful navigation and scientific investigation. Its tracks stretched across imagery taken by orbiting spacecraft, a line drawn on Mars by something made on Earth, marks that will fade only slowly in the thin winds and will remain visible for centuries or longer. Opportunity's final transmission came in June of 2018, when a global dust storm starved its solar panels of light and the rover fell silent forever. A long road walked, a long mission finished. The Curiosity rover landed in 2012 and is still exploring Gale Crater, climbing the slopes of Mount Sharp. In August of 2012, a rover unlike any before it descended through the Martian atmosphere on a daring sky crane maneuver, lowered by cables from a hovering descent stage that flew away after depositing its payload on the floor of Gale Crater. An arrival so complex that engineers at NASA called the landing sequence 7 minutes of terror. Yet everything worked perfectly, and Curiosity rolled onto the surface to begin a mission that continues to this day. Larger than a small car and equipped with a suite of instruments, including a laser that can vaporize rock from a distance, Curiosity has spent over a decade climbing the slopes of Mount Sharp, reading the geological history recorded in its layered sediments. It has found organic molecules, measured radiation levels, and greatly expanded our knowledge of ancient Mars. Still climbing, still discovering. Curiosity is powered by a nuclear battery that will keep it running for many more years to come. Unlike the solar-powered rovers that came before it, Curiosity carries a radioisotope thermoelectric generator, a power source that converts the heat from decaying plutonium-238 into electricity, providing a steady supply of energy day and night during dust storms and polar winters, independent of the sunlight that so often fails earlier rovers. This nuclear battery is expected to provide useful power for at least 14 years from landing and possibly longer, allowing Curiosity to continue operating through conditions that would have shut down its solar-powered predecessors. The independence from sunlight has also allowed Curiosity to work through the night when other missions would be dormant, and to survive the dust storms that ended Opportunity's mission. A heart that beats with atomic warmth, power measured in decades. The Perseverance rover landed in 2021, carrying instruments to search for signs of ancient microbial life. Building on everything learned from previous missions, the Perseverance rover touched down in Jezero Crater on the 18th of February 2021, alighting in an ancient river delta where conditions may once have been ideal for life, equipped with the most sophisticated instrument suite ever sent to Mars, specifically designed to search for biosignatures, chemical traces that might indicate whether living organisms ever existed on the red planet. Perseverance is also collecting rock samples that will someday be retrieved by a future mission and returned to Earth for detailed analysis in laboratories, the first step in a multi-decade effort to bring pieces of Mars home for study. The delta it explores was once the mouth of a river flowing into a lake, a perfect place to look for fossils of ancient microbes. Ingenuity, a small helicopter carried by Perseverance, became the first powered aircraft to fly on another planet. Tucked beneath the belly of Perseverance for its journey to Mars was Ingenuity, a small rotorcraft weighing less than 2 kilograms, designed as a technology demonstration to determine whether powered flight was possible in the thin Martian atmosphere. And in April 2021, it rose a few meters above the surface and hovered for nearly half a minute, becoming the first aircraft ever to achieve powered, controlled flight on another world. What was designed as a brief experiment expanded into dozens of flights, scouting terrain ahead of the rover and demonstrating capabilities that will influence the design of future missions. The thin atmosphere that makes flight difficult also reduces drag, and Ingenuity's twin rotors spun at more than 2,000 revolutions per minute to generate lift. The Wright brothers' legacy extended to Mars, first flight on a world beyond Earth. And from the rovers that crawl across the Martian surface, we now turn to one of the oldest and most profound questions: could there be life on Mars? No definitive evidence of life has ever been found on Mars, but scientists continue to search with every new mission. Despite more than half a century of robotic exploration, sending orbiters and landers and rovers to examine the Martian surface and subsurface with increasingly sophisticated instruments, no definitive evidence of life, past or present, has ever been confirmed on Mars, and the red planet remains as enigmatic as ever regarding the question that most captures the public imagination. This absence of proof is not proof of absence, as scientists are careful to note, for we have examined only tiny fractions of a vast world, and life, if it exists or existed, may be hiding in places we have not yet looked, in subsurface aquifers or ancient sediments not yet sampled. Each new mission carries instruments more sensitive than the last. Each new landing site is chosen for its astrobiological potential, and the search continues with undiminished hope. The question remains open. Mars has not yet revealed its deepest secrets. If life ever existed on Mars, it most likely would have been microbial, living in water or beneath the surface. No one expects to find complex organisms on Mars, no fossils of fish or forests or civilizations buried beneath the dust. For even in its youngest and warmest era, the planet was probably never hospitable enough for multicellular life to evolve. But if anything ever lived there, it would most likely have been microbial, single-celled organisms similar to the bacteria and archaea that dominate Earth's own tree of life. Creatures that could thrive in water or damp soil or the dark recesses beneath the frozen surface. Such microbes would leave few traces visible to the naked eye, requiring sophisticated chemical analysis to detect, and they might have persisted underground long after the surface became inhospitable, perhaps even surviving to the present day in pockets of liquid water or briny seeps. The search for Martian life is a search for the small and the subtle, traces written in chemistry rather than stone. Methane has been detected in the Martian atmosphere in small amounts, a gas that on Earth is often produced by living organisms. Several spacecraft and ground-based observations have detected small amounts of methane in the Martian atmosphere, a gas that on Earth is primarily produced by biological activity, from the digestion of cattle to the metabolism of microbes in wetlands and seafloors, raising the tantalizing possibility that something might be releasing this gas on Mars as well. However, methane can also be produced by geological processes, by reactions between water and certain minerals deep underground, and distinguishing between biological and abiotic sources requires measurements more precise than any yet obtained. The methane also appears to vary over time and location in ways that are difficult to explain, adding to the mystery rather than resolving it. A hint, not a conclusion. A question mark floating in the thin Martian air. The Perseverance rover is collecting rock samples that will eventually be returned to Earth for more detailed analysis. One of the primary goals of the Perseverance mission is not just to analyze rocks on Mars, but to collect carefully selected samples and seal them in tubes that will be retrieved by a future mission and returned to Earth, where laboratories far more capable than anything that can be sent to Mars will examine them in extraordinary detail, searching for signs of ancient life, measuring isotopes, and characterizing mineralogy with precision impossible to achieve remotely. This Mars sample return project is one of the most ambitious endeavors in the history of planetary science, requiring multiple spacecraft and more than a decade of development. But if successful, it will bring pieces of another world into human hands for the first time since the moon landings. The samples wait in their tubes, a promise of future knowledge. If microbial life is found on Mars, it could suggest that life arises easily wherever conditions permit, even across the cosmos. The discovery of even the simplest life on Mars would be one of the most profound scientific findings in history, not only because it would tell us that we are not alone in the universe, but because it would suggest that life arises readily wherever conditions allow, that the origin of life is not a rare and improbable accident, but a natural consequence of chemistry given time and energy and the right ingredients. If life began independently on two planets in a single solar system, it would imply that the cosmos is probably teeming with living worlds, that the galaxy and beyond are filled with biology in forms we cannot yet imagine. This is the reason the search for Martian life continues with such urgency. One microbe would change everything, a single cell rewriting our understanding of the universe. And with these thoughts of ancient life and distant possibilities, let yourself breathe slowly in and out, like the faint whisper of wind across a Martian plain. There is nothing to solve tonight. Just rest and let the mystery carry you gently towards sleep. Some scientists believe that if life exists on Mars, it may be hiding deep underground, protected from radiation and cold. The surface of Mars is a harsh place, blasted by ultraviolet radiation, scoured by oxidizing chemistry, frozen most of the time and only rarely warm enough for liquid water. But beneath the ground conditions may be very different, more stable temperatures, shielded from radiation by meters of rock, and possibly access to liquid water in deep aquifers or geothermally heated zones. Some scientists speculate that if life ever arose on Mars and still persists today, it is most likely to be found not on the surface, but in these deep refuges, where Earth-like microbes called chemolithotrophs might extract energy from chemical reactions between rock and water, living in darkness as similar organisms do deep within Earth's crust. Reaching such depths is beyond our current technology, but the depths might be where the answers lie. Caves and lava tubes on Mars could provide shelter for future human explorers, just as they might for any Martian life. Scattered across the volcanic regions of Mars are openings in the ground that may lead to extensive lava tubes, underground passages left behind when flowing lava drained away and left hollow tunnels, structures that on Earth can stretch for kilometers, and that on Mars, where lower gravity allows larger spans, might be even more extensive. These tubes could provide natural shelter from radiation, temperature extremes, and micrometeorite impacts, requiring only sealing and pressurizing to create habitable spaces far safer than anything built on the exposed surface. If life exists on Mars underground, these same tubes might harbor it, their dark interiors offering protection and stable conditions. A home waiting to be claimed, shelter carved by ancient fire. Several space agencies are planning crewed missions to Mars, with goals to land humans on the red planet within the next 2 decades. After decades of robotic exploration, human missions to Mars are now seriously planned by multiple space agencies and private companies, with target dates in the 2030s or 2040s for landing the first astronauts on the Martian surface, a goal that would mark the farthest journey humans have ever undertaken from Earth. Months of travel followed by possibly years of residence before the planets align for a return journey. The technical challenges are immense, from life support systems that must function for years without resupply to psychological support for crews isolated beyond any hope of quick rescue. Yet progress continues and confidence grows that these obstacles can be overcome with sufficient investment and determination. Humans may yet walk on red soil, the first footprints on a world beyond the moon. The journey from Earth to Mars takes roughly 7 months, using current rocket technology. With present-day propulsion systems, a spacecraft traveling from Earth to Mars follows a curving trajectory called a Hohmann transfer orbit, a path that minimizes fuel requirements by using the gravitational pull of both planets to swing the vessel from one orbit to another, a journey that typically takes between 6 and 9 months, depending on the relative positions of the planets at departure. During this transit, astronauts would be exposed to cosmic radiation, confined in limited space, and unable to return quickly if anything went wrong. Months of isolation before the red horizon finally grew large enough to fill the window. Future propulsion technologies might shorten this journey, but for now the crossing remains long and lonely. 7 months between worlds, a voyage measured in patience. Future Mars colonists would need to produce their own food, water, and oxygen, relying on resources found on the planet itself. Sending supplies from Earth to Mars is so expensive and time-consuming that any permanent settlement will need to become largely self-sufficient, producing food in greenhouses or bioreactors, extracting water from ice deposits in the soil, and generating oxygen from the carbon dioxide atmosphere or from electrolyzing water, a practice called in situ resource utilization that would reduce dependence on the home planet and make long-term habitation possible. Early colonists would need to establish these production systems before their supplies ran out, racing against time to bootstrap a functioning closed-loop habitat on an alien world where a single critical failure could prove fatal. The challenge is immense but not impossible, living off the land, just on a different land. Terraforming Mars to make it habitable for humans would take centuries, if it is possible at all. Some visionaries dream of transforming Mars over centuries or millennia into a world where humans could walk outside without spacesuits, breathing air and feeling rain on their faces, a process called terraforming that would require thickening the atmosphere, warming the climate, and introducing water and perhaps engineered organisms to create a biosphere from scratch. The scale of this undertaking is almost beyond imagination, requiring resources and timelines that stretch far past any planning horizon we can take seriously today, and some scientists doubt whether it is even physically possible given the loss of the magnetic field and the continuing escape of atmosphere. Yet the idea persists, a dream for future generations, centuries of work toward a second Earth. Mars has valuable resources, including iron, silicon, and water ice, that could support a permanent human presence. The red surface of Mars is rich in iron oxide. The regolith contains silicon and aluminum and other elements useful for construction, and the ice deposits scattered across the planet provide water that can be used for drinking, for agriculture, and for splitting into hydrogen and oxygen for rocket fuel, a collection of resources that could, in principle, support a permanent human presence without constant resupply from Earth. Mining and refining these materials would require machinery and energy, but all the basic ingredients are present, the raw materials for a civilization waiting to be extracted from the dust. Future settlements might eventually become exporters rather than importers, a world that could sustain those who come to stay. Communication between Earth and Mars can take up to 20 minutes each way, meaning astronauts would need to solve many problems on their own. The distance between Earth and Mars varies from roughly 55 million to more than 400 million kilometers, depending on where the planets are in their orbits, and signals traveling at the speed of light take between 3 and 22 minutes to cross that gulf, meaning that a message sent from a Martian settlement would not receive a reply for at least 6 minutes in the best case and nearly 45 minutes in the worst. This communication delay rules out real-time conversations, makes remote control of machinery impractical, and means that astronauts facing emergencies would be largely on their own, unable to consult with mission control and receive answers in time to be useful. Self-reliance would not be optional. Decisions would need to be made alone. And from dreams of future colonies and human footprints on red dust, we now come to rest with the quiet beauty of Mars as it is, still, ancient, and endlessly waiting. The night sky on Mars shows 2 tiny moons and a star-filled expanse, with Earth visible as a small blue dot near the horizon. If you could stand on the Martian surface after sunset and look up, you would see a sky filled with stars far more numerous than what city lights allow most people on Earth to observe, the thin atmosphere scattering little light and leaving the cosmos brilliantly visible, while near the horizon, a faint blue dot would mark the position of your home planet, tiny and distant, yet unmistakably present, just as Mars appears as a red dot from Earth. Phobos might race across the sky if the timing were right, and Deimos would hang motionless for hours, but it is that pale blue dot that would hold your attention, everything you have ever known reduced to a point of light, no brighter than many of the stars around it. Home seen from exile, a small blue spark across the darkness. Sunrises on Mars cast long shadows across the crater rims, blue light filtering through the dusty atmosphere. As the small disk of the sun climbs above the Martian horizon each morning, its light filters through kilometers of dusty atmosphere, scattering into the distinctive blue glow that surrounds it, while the landscape below awakens in shades of rust and shadow, long dark lines stretching from every boulder and crater rim as the low-angle light picks out every detail of the terrain. The shadows retreat as the sun climbs higher, the colors shifting from the blue-touched tones of dawn toward the pink and butterscotch of midday, and the temperature slowly rises toward levels that might almost be comfortable before beginning its plunge back toward the deep cold of night. Morning on Mars is a slow affair, light painting the red land in gentle stages. In the silence of Mars, there is no birdsong, no rustling leaves, no ocean waves, only the faint sigh of wind across stone. Mars is a world of profound silence, where no birds call across valleys and no waves break upon shores, where no voices have ever traveled through the thin air and no engine has ever disturbed the stillness. Only the faint whisper of wind moving dust across rocks that have rested undisturbed for billions of years. The thin atmosphere carries sound poorly, and what little noise there is would be high-pitched and faint to human ears, nothing like the rich soundscape of Earth with its rustling forests and crashing surf and distant traffic. Standing on the Martian surface would mean standing in a quietude more complete than almost anywhere on Earth, broken only by the sounds you bring with you. Silence as old as the planet, stillness without end. Mars has orbited the Sun for over 4 billion years, long before life arose on Earth, watching our world from across the void. For more than 4 billion years, Mars has traced its patient orbit around the Sun, circling in the darkness while dynasties rose and fell on Earth, while single-celled life evolved into fish and forests and civilizations, while mountains lifted and eroded and lifted again, all of it occurring on a small blue world that Mars has watched from afar, a dimly visible dot in its own night sky, never knowing what changes were unfolding beyond the void. And now, at last, creatures from that distant world have sent emissaries, robots that crawl across the red dust and photograph the ancient hills, preparing the way for something more. Mars waited, and finally something came. And still Mars waits, patient, quiet, and full of secrets yet to be discovered. After billions of years of silent existence, after centuries of human telescopes and decades of robotic visitors, Mars remains a world of mysteries, its ancient riverbeds unwalked, its deep caves unexplored, its questions about life and origins unanswered, holding secrets in its rust-colored soil that we have barely begun to uncover. Future missions will dig deeper and range farther, and perhaps someday human beings will set foot on that orange-red ground and begin the work of truly understanding this neighbor world. But for now, Mars remains what it has always been, a quiet presence in the night sky, watching and waiting as it has waited since before the first ocean formed on Earth. The waiting continues, the patience of a planet measured in eons. And so our journey across Mars draws softly to a close as the red dust settles once more into stillness beneath the pale Martian sky. From the rust-colored plains that stretch to every horizon to the towering peak of Olympus Mons rising silent above the clouds. From the ancient canyons that carve deep into the Martian crust to the frozen poles where water ice waits beneath carbon dioxide frost. From the small, misshapen moons that drift through the Martian night to the robotic explorers that carry our curiosity across a world no human foot has touched. These are the quiet wonders of the Red Planet, a world both familiar and impossibly distant, yet connected to us by the same sun, the same stars, and the same deep longing to understand what lies beyond our own pale blue horizon. If these gentle facts brought you comfort tonight, consider joining us for the next journey by subscribing. There are more wonders waiting, sleeping giants on distant moons, the secrets of ancient galaxies, and the quiet truths hidden in the world all around you. Together, we are building something gentle, one sleepy soul at a time. Right now, as you lie here listening, Mars is out there, somewhere beyond the boundaries of our sky, its red desert stretching beneath unfamiliar stars. The same light that touched its dusty plains earlier today will travel for many minutes before reaching your eyes, if you were ever to look up at that faint red dot drifting among the constellations. You carry within you the same atoms forged in ancient stars, the same matter that makes up the rust-colored rocks of that distant world. In some small way, you are already connected to Mars, as all things in the universe are connected to each other. Now let your eyelids grow heavy if they wish to close. Let your breathing slow, each exhale a little longer than the last, like the gentle rhythm of wind across Martian dunes. Let your shoulders release any lingering tension, your jaw soften, your hands uncurl. There is nothing left to think about, nothing left to do. Just let yourself drift, carried gently by the quiet of this moment, like dust settling on a world where time moves slowly and the silence is ancient. Tonight, as you rest, Mars continues its quiet orbit around the sun, its volcanoes sleeping beneath pink skies, its frozen poles glistening faintly in the starlight. Rovers continue to crawl across its dusty surface, photographing rocks and measuring the thin air. The canyons stretch in darkness, unchanged for millions of years. And far beneath the surface, perhaps, ice waits in silence for a future we cannot yet imagine. You are a small, warm presence within this vast cosmic neighborhood, peacefully resting among the wonders. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that somewhere, far beyond the edge of our sky, a red world waits in silence, full of secrets older than the mountains and more patient than the stars. This has been Drowsy Discovery. Good night.